Thank you all for coming this week. I guess I should say for attending this week. So this is I lost track of how many of these applied PD seminars we've done this quarter, but this week we have Bobby Wilson from the University of Washington. Of course, if we didn't have a pandemic going on, there's no way we would have this be a virtual seminar, but here we are, and so there's at least the benefit that people from far away can attend as well. Bobby got his PhD from the University of Chicago in 2015 under the direction of Willem Slaag. He then went on to MIT, where he was a C.L. Moore instructor, and then he's been an assistant professor here in the mathematics department at the University of Washington since 2018. So today he's going to tell us about the stability of the cubic nonlinear Schrodinger equation on irrational tori. Thank you, Bobby.
Thank you very much for the introduction. Thanks for having me here. I am happy to be speaking about this topic today because I've been thinking about it for a long time, the nonlinear Schrodinger equation, since I was a graduate student, but also recently Gigliola and I have begun working with someone who's not a pure mathematician by trade. Yulin is in the naval architecture and marine engineering department at the University of Michigan, and last summer essentially Gigliola noticed that he was also a postdoc at MIT while I was there, although we did not meet, and she decided to bring us all together and do a kind of a interdisciplinary project related to what Gigliola and I had already been studying before. And it was very nice. It was very refreshing to see some of the numerical simulations, which I'll show a little bit of, but I am now in no way very knowledgeable about what goes into these simulations, or I guess what is what's expected in some sense. So I'll try to be in this lecture. I'll try to be informal with the pure mathematics, and rely a little bit more on a little bit more of a colloquial kind of explanation of what we're doing on the mathematics side, and also try to lean on pictures and things like that. So hopefully I won't be too pedantic with the math thing. So let's begin. First of all, I think I have to do this since this is an applied math talk. I have to at least mention the physical models associated with the cubic nonlinear Schrodinger equation, which we'll talk about today. When I first started studying dynamics of dispersive equations, I knew nothing really of the physical model or the physics that it was trying to describe, and so I've learned essentially by osmosis over the years, and particularly I saw a talk, I think this is 2 weeks ago now, by Natasha Pavlovich in the MSRI connections workshop that's associated with the fluid dynamics semester that they're running this semester, and Natasha did a very good job of, in all of her talks, but in particular this one, of explaining exactly the transition between the physical models of particles in a gas, going from that to the Gross-Patevsky hierarchy, and then from that the factorization that gives you cubic, but in her talk in particular she talks about quintic nonlinear Schrodinger equations. So this stuff I'm learning very I don't know, slowly, but I think it's very interesting, and she and her collaborators really their goal or one of their research directions is really to make this connection very mathematically sound. And also, again, I don't know a lot about the physical models, but my understanding from Schneider's book on nonlinear optics and telecommunications is that there is some way to go from a physical model or some physical understanding of the way light goes through certain media to the cubic nonlinear Schrodinger equation. But I'm learning this bit by bit, and yes, I couldn't possibly sum it up, so I'll just leave it at that. And I guess there was a talk in November in this seminar about this, but about in particular this type of representation. Okay, so what I'll do is I'll introduce essentially the model that we're looking at. We're looking at an evolutionary equation. This is the cubic nonlinear Schrodinger equation, and to pick the in particular the Cauchy problem. My physical space is compact, so I'm looking at the d-dimensional torus, and what I'll describe as the irrational Schrodinger nonlinear Schrodinger equation is particularly when we rescale the aspect ratio for a flat torus so that the aspect ratio is irrational. But we'll describe this in detail later. Yes, and I guess I should notice also that we're considering the defocusing equation for the purposes of what we are looking for, the dynamical systems questions that we're asking, and we'll discuss in this lecture. Defocusing and focusing don't play, whether you're defocusing or focusing doesn't play a humongous role. Okay, so what is an irrational nonlinear Schrodinger equation? I take the flat torus, okay, which is just R mod Z. I take the flat torus, or you can call it S1, and then the d-dimensional flat torus. And typically our D will be 2 in this lecture. And well, typically, but actually from here on out, really, you can think of D as just equal to 2. That's enough to get a irrational torus. But essentially, we're taking the torus, we're rescaling it, so that its aspect ratio is irrational. And in particular, maybe the best way to think about the scaling being irrational is that we're in particular scaling the Laplace-Beltrami operator. So we don't care that the vector that we're scaling the torus by is irrational, but we care that the square of the vector is irrational. And this square of the vector corresponds to the scaling that we do for the scaling that you get in the Laplace-Beltrami operator. So it's a little bit of a misnomer because I'm taking the square and asking for that to be irrational. And this is the typical definition of irrational for a vector in R, meaning that any integer linear combinations of your components is never 0, non-trivial. So non-trivial linear combination over Z. Yes, okay, so we are rescaling our torus, and it would seem that this would not matter too much, but let's talk a little bit about some history and why we care about higher dimension versus let's say 1 dimension, why we care about D equals 2 and not D equals 1. One can show that for the 1 dimension, or when you define the nonlinear Schrodinger equation, in particular the cubic nonlinear Schrodinger equation, and your physical space is 1-dimensional, the 1-dimensional torus, that this is a completely integrable system, meaning that you can find a change of variables so that all of your solutions are either, you can find a change of variable that demonstrates that all of your solutions are either periodic, quasi-periodic, or almost periodic. Okay? And this is the kind of a colloquial way of defining it. And geometrically, let's say it means that you can foliate space, phase space into these leaves and these tori in which all of your solutions stay on these submanifolds, so Lagrangian submanifolds. I guess you wouldn't call them Lagrangian because it's Birkhoff integrable, not Liouville integrable. But regardless, you can foliate your space into these manifolds in which your solutions start on the manifold. If your solutions start on a certain manifold, they must stay on this manifold. Okay. For infinite dimensional systems, it's a little weirder to think about, but for finite dimensional systems, it's not so crazy. You think of, let's say, R2, and then you foliate it or you decompose it into basically circles. This is essentially what you're doing. Okay. For D equals 2, it's a harder question, the dynamics of, or in particular, even if it's well posed. So in 1970, you have not only that you have a well-posed system, that means that you have a continuous, you have a continuous dependence on your initial data, and time, your solutions can be defined at least continuously. And of course, if you are integrable, then the solutions have much more regularity in time. But for d equals 2, you can show with very, what should I say, sophisticated harmonic analysis. Again, was able to show that for d equals 2, you have global well-postedness, and this is much weaker than complete integrability, excuse me. But you have global well-postedness, meaning that you can find a solution that's continuous in time to the nonlinear Schrodinger equation. Okay, and this is for any rational torus. So essentially, any torus that can be rescaled, or it can be scaled with a rational vector. And again, I have to be a little careful here. There is not my construction of a rational torus, or my definition of a irrational torus, and my definition, I guess what you can suppose the definition of a rational torus, they do not cover all cases. Okay, so I'll let my irrational torus, let me go back for a second, my irrational torus be defined this way, but my rational torus, I want the actual vector, not the square vector, to be rational. And the reason is that the argument for this well-postedness essentially goes in this way. You can show that any square torus, okay, that means that your aspect ratio is essentially 1. So any square torus, you can demonstrate well-postedness. And then for a rational torus, what you do is you essentially tile your square torus with any rational aspect ratio torus, or box, let's say. And since you can tile your square torus with a rational torus, for any rational, for a big enough square torus and any rational torus, that means that you can actually reduce the argument to a well-postedness argument on a aspect ratio of 1. And for this simple reason, it becomes impossible to do it for an irrationally scaled torus, or irrational aspect ratio. So it's pretty. I think it's a little bit I don't know, weird that and we'll see for a very long time there was no way to, and it's an interesting curiosity that there was no way to actually very simply rewrite or deploy the tools that Bergan showed in 1993 to prove well-postedness when your torus, or where your physical space is merely rescaled in this kind of funny way. But it turns out it was, and it turns out that it takes even more sophistication than what Bergan did in 1993. So in 2014, Bergan and Shipley and Demeter, they show that if you have a irrational torus, and you can get an estimate, an harmonic analysis estimate that's very similar to the one before, but it's a little bit more powerful. Okay, and I have these estimates here. They're not so important. Again, I promise that I'll be a little bit more colloquial here. The estimates are there just for precision's sake, but essentially what this amounts to is that you can show more things than the application to the nonlinear Schrodinger equation. But in particular, for the nonlinear Schrodinger equation, you can show that for any scaled torus, you have global well-postedness. Okay, so it took 21 years and a lot of and much more development in harmonic analysis to demonstrate that this curiosity is merely a curiosity, that it doesn't really matter how you scale your torus, you still have a well-defined flow for your evolution equation. Okay, so it's weird, but one could ask, is there something more interesting happening when you rescale your physical space, so that you have a box or a torus, let's say, that has an irrational aspect ratio? And these types of things do appear in dynamical systems sometimes, but in this case, it's yeah, it's kind of surprising, I suppose, to expect that it would be very different. So let me discuss a little bit about how where I started in this particular weird irrational versus rational dichotomy. When I got to MIT, I was speaking with Gigliola about the case the case of what they call infinite energy. Okay, so and this is the case where you have a nonlinear Schrodinger equation, but your phase space requires so little regularity that the typical Hamiltonian that you define with this corresponds to your equation, that particular Hamiltonian is not necessarily a bounded function on phase space. So you can have functions, or you can have points in phase space for which the Hamiltonian is not finite, which kind of destroys all of your well, it destroys a little bit of your intuition, but it also destroys your structure that you're relying on to show, for one, integrability from Zakharov and Shabbat, but other nice kind of dynamical properties of a system. Okay, and so in the infinite dimension, infinite energy case, and I'm assuming that my S is less than 1, I should maybe say a little bit about this, and maybe yes, I'll go back here, and even here, I have my initial data in HS, and I said that I would try to be a little bit colloquial here. My HS is essentially the L2 Sobolev space, so that well, it says that my function has S derivatives, let's say. Okay, and so when I assume that I have more than one derivative, then I am in a very my phase space has very regular data, let's say. And when I assume that I have less than one derivative, or I have fractional derivatives at least, then my phase space is such that my Hamiltonian, or the points in the phase space, are not regular enough to ensure that my Hamiltonian is actually finite. Okay, so the question that people who do harmonic analysis apply to dispersive PDEs ask themselves is, okay, well, you can show nice results for the case where you have a Hamiltonian structure, where you can impose a symplectic structure in phase space. You can define a Hamiltonian that has a flow that's equivalent to that of the nonlinear Schrodinger equation, the cubic nonlinear Schrodinger equation. This is all well and good. What if you just simply have a weakly defined solution to the nonlinear Schrodinger equation with no energy that allows it to have a nice dynamical properties, very kind of simple local apoptosis and things like this? Do you still have, in some sense, an existence of solutions, unique existence of solutions for all time? So the first, yes, I believe the first attempt at this was De Silva, Pavlovich, Staffilani, and Zerakis in 2006, which showed that if your regularity is high enough, meaning that you have more than 2/3 of the derivative, and I apologize for speaking about fractional derivatives or anything like this. This is the fastest way I can describe it. But if you have more than 2/3 derivatives, then you do have a bilinear structure estimate that leads to global well-postedness. This is what I mean by GWP. Okay, so and it is a, let's see, a program, let's say, among people who do harmonic analysis, and even people who do probability with apply probabilistic methods to well-postedness for evolution equations. It's a program of finding essentially what's the least amount of regularity that's necessary to have global well-postedness, or have a actual unique existence of a solution for a Schrodinger equation. Okay, but concentrating just on the 2006 result from the four there, they were able to show, using very similar techniques and machinery that Bergan developed in 1993, they were able to show that using bilinear structure, as I said that before, but that if your torus is a rational torus, it has a rational aspect ratio, then the minimal regularity necessary, or you need at least, or you can go down to 2/3 fraction, or 2/3 derivatives to show well-postedness. And so, again, my introduction to this problem was in 2016, really, where we worked with one of Staffilani's former graduate students and one of Larry Gutz's former graduate students to demonstrate that even for the irrational torus using the machinery of Organ and Demeter in 2014, that you can show that, again, you have global well-postedness for this small amount of regularity. Okay, again, not using the Hamiltonian and the structure you get from being in a symplectic manifold, even though it's maybe an infinite dimensional symplectic manifold, you're still able to use that kind of structure to control your dynamics of your system. But without that, you can still show that you have global well-postedness. Okay, so again, it would seem so far that although you can, or although it's harder, although you can show global well-postedness for exactly the same situations for the irrational torus as the rational torus, there seems to be something happening for the irrational torus that may or may not be happening when your aspect ratio is rational. Okay, and in particular, the question that we asked ourselves after we did global well-postedness, and this was kind of thought about for some other results as well, and I'll describe those as well. And the question essentially is, are the dynamics the same? Okay, can you say the exact same things that you can say in the two-dimensional rational case that you can in the irrational case? And in particular, as I mentioned before, for the dimension 1 cubic nonlinear Schrodinger equation, one can show that you have an integrable system. Okay, again, all solutions are either periodic, quasi-periodic, almost periodic. For the two-dimensional equation, okay, and I have one there. I have the solution to one, but of course one was shown a long time ago. But that's the two-dimensional equation, and I'm assuming d is equal to 2 or higher. For the two-dimensional equation, for high regularity phase space, okay, your S is great. You have more than one derivative at least. One can show that, or demonstrate to some extent, that you are not integrable, in the sense that you can show that you can start off with very low regularity after your initial condition, or sorry, very low energy in HS, let's say. You can start off with very low energy and then increase to an arbitrarily high energy. Okay, and so this is kind of antithetical to the concept of a periodic solution or a quasi-periodic solution, let's say. Right, a periodic solution, you cannot show, let's say if all solutions were periodic, you wouldn't be able to show that you could start off with an arbitrarily high. Okay, this is not exactly true, but most of the time, one can show that at least very close to the origin, that if you start off with a very small HS norm, then your HS norm should be essentially small for all time. Okay, you're essentially a harmonic oscillator going around the origin forever. Okay, and if you're quasi-periodic, it's some higher dimensional version of this. Of course, there are situations where you can show that you have growth of Sobolev norm even when you're integrable, but generally speaking, the rule of thumb is that if you do have an integrable system, then your HS norm should be more or less conserved. Okay, but in this case, it's not. In the d equals 2 case, and the d equals 2 and higher case, the nonlinear Schrodinger equation demonstrates that you, to some extent, possibly do not have integrability. Okay. Okay. So the question that was, I think, originally Gigliola asked was, is it the same? Do you have the same type of dynamics for the irrational torus, high dimensional torus? Okay. So if you ask the same questions, you're in a high regularity space, you're in HS or S bigger than 1. Your torus is aspect ratio is irrational. Can you demonstrate that you have some type of non-integrability in the sense that of this paper here, or this result here? Okay, and so we looked at that. Okay, and here's the Hamiltonian. Again, we're in a high regularity phase space, so we can define the Hamiltonian at this point. You see the lambda k is our dispersion relation, and this is essentially why I care about having my my irrational or my vector or my scaling be irrational with respect to its square. Here you have oops, I did not mean to do that. Here you have your square, and this is essentially how the Laplace Beltrami operator is being scaled with respect to the actual just linear scaling on your torus. And this is just more or less an informational slide, but exactly the Hamiltonian I'm looking at, and in particular that I care mostly about the Fourier coefficients of my solutions more than I care about the actual solutions. I like to think of all of these, even the original nonlinear Schrodinger equation, and purely in terms of Fourier coefficients. And so here's the Hamiltonian, and then your phase space is HS. Okay, and then I have a little HS, and this corresponds to sequences. But this little HS corresponds to the class of Fourier coefficients or Fourier sequences of solutions or functions, excuse me, in big HS. Okay. So again, the question is, do you have the same type of dynamics? In particular, do you have a lack of integrability in the irrational case, as you do in the square case? And in order to pursue or in order to demonstrate whether or not you have integrability or not, it's common to do a normal form transformation. And even in the finite dimensional case, I have a finite dimensional, I guess, representation of a normal form. But essentially, we would like to say that one can, with successive changes of variables, one can write your Hamiltonian in such a way that it becomes very obvious that all of your solutions are either periodic, quasi-periodic, or almost periodic. Essentially, you want to, this is maybe a poor way to state it, but you essentially want to linearize your equation. It's not exactly linearization, but it's somehow decoupling of the different modes of, say, the Fourier modes from each other, so that their dynamics are completely decoupled. But there are many ways to kind of think of this, and this is one here that your Poisson bracket or your Poisson commute with the linear part of your Hamiltonian or the quadratic part of your Hamiltonian to be specific. Okay, a very important notion when it comes to dynamics of finite dimensional Hamiltonian systems, but also infinite dimensional Hamiltonian systems, or whether your dispersion relation or your frequencies that are associated with your quadratic part of your Hamiltonian. And these are very, I will admit that this is a very special class of Hamiltonians, which with elliptic fixed points at the origin. But okay, that's a different story. But an important concept is whether or not you have a non-resonance of your quadratic frequencies, or the frequencies of your quadratic part of your Hamiltonian, or the frequencies that are given for the or elliptic frequencies that are associated with your fixed point 0. And we'll say this is non-resonance essentially if a very similar concept to irrational, essentially, that essentially integer linear combinations are never 0, as long as your actual you have a non-trivial linear combination. Okay. Okay. So I say this all to say, essentially, what we would like to do in order to examine the dynamics of the irrational or the nonlinear Schrodinger equation defined on an irrational torus is we want to do a normalization procedure to, and this is a similar but not exactly what is done in the paper, and I should say, or the paper or the result that demonstrates you have non-integrability for the two-dimensional nonlinear Schrodinger equation, cubic nonlinear Schrodinger equation. They do, to some extent, do a normalization procedure and then look at a model equation, but it's not exactly in the way that I'm describing here. Okay, so this is a theorem from Moser in '68, and of course, Moser is interested in celestial mechanics, and essentially what you can do is that in the finite dimensional case, let's say you have your quadratic part is a nice, your quadratic part for your Hamiltonian is a nice well, it has a nice form. I'll say you have your frequencies, your omega j here. You have your pj squared plus your qj squared divided by 2 for non-obvious reasons. You have a cubic or a 0 order 3. So it's a Hamiltonian in itself as well, but it's a perturbation really of your quadratic part of your Hamiltonian. And so let me clear this up a bit right now. Typically, I'll say H0 is the linear part of your Hamiltonian, and the reason is because the Hamiltonian vector field associated to this Hamiltonian H, its linear part is essentially has a one-to-one correspondence with H0. And it's given completely by what H0 is, assuming, of course, that P has a 0 order 3 at the origin. Okay, so what am I saying here? Moser says that regardless of what Hamiltonian you have, you can normalize your Hamiltonian up to a certain order with a symplectic morphism, essentially. So something that a change of variable that preserves your symplectic structure. That's invertible. It's very nice. It's actually analytic, and so at least in a neighborhood of the origin. Okay. Now, as you continue to do higher and higher normalizations, more and more normalizations, the neighborhood around your origin can converge to 0, but that's completely fine. A lot of the information, a lot of the dynamical information that you can get from normalization only can be, I guess, gleaned just from the first few terms of your normalized system. So so it actually it's very common practice to only do a few changes of variables before stopping to kind of understand exactly what that tells you about the dynamics of the system. So okay, so this is just again an explanation of exactly kind of what is expected and what one can do when given a system, a Hamiltonian system, and one would like to know about the dynamics of the Hamiltonian system. Okay, let's see, and this is more or less formal, but saying essentially that if your omega is non-resonant, you can say very nice things about the dynamics. Essentially that if you start off very close to 0, then after a long time, you will still be very close to 0. And if you take higher and higher order normalizations, you can say that it's close to 0 for a longer and longer time. Okay, and which is exactly, again, antithetical to what the result for the two-dimensional rational cubic nonlinear Schrodinger equation, which says that you can construct a solution that starts off very small and gets arbitrarily high in HS naught. Okay, after a certain amount of time. Okay, this is completely opposite of that. All right, so we don't have a finite dimensional system. Okay, we have an infinite dimensional system, and we would like to use or extrapolate the theory from Moser to infinite dimensional systems. And the first thing that Gigliola and I did, and this is a common thing to do in general, but actually to do a harder version of this, but what one does, excuse me, is essentially take your system that has infinitely many variables, and then cut off after a certain height all of your variables. So you take the tails and you say, I'm going to throw them away. They're very small. Okay, I'm taking an infinite sum, so eventually the tails get very small. and I'm going to say, I'm going to throw that away. I'm going to put it into a perturbation. I'm going to say this is actually just a perturbation of my system. If I can cut off my system, my infinite dimensional system, into a finite dimensional system plus a perturbation. Okay, that happens at infinite dimensions. And so you can do that, and there are some limitations to what one can say. You can Taylor expand, let's say in the high variables here. Oh, I have a z here. I think this needs to be a u hat, but that's fine. We can do a change of variables in the sense of Moser, and then you can get your homological equation here. I didn't really explain what the homological equation is, but this is really fun. Then you have a normalized part z. Okay, and this normalized part corresponds to the normalized part here. Okay, and this is only one step, just one step here. You have one step, and then you still have higher order terms, or lower order terms, excuse me. Still have terms of order 3 that you have not normalized, but all of these all of these non-normalized terms have a factor of z to the h, and z to the h, or u hat to the h, let's say, is assumed to be small, okay, because it's the tail of the sequence. Okay, so what do you get? And what are the, okay, so after you've done this normalization, you would like to then, the next step of the process is to examine the dynamics of the normalized system, okay? And so our z here is a normalized part. We have cutoff at height n, and the sum, somehow the sum of or what the elements you're summing over determine completely the dynamics of the system here. So these are all of my resonant vectors. Okay, so let me. I won't backtrack. I'll just say that these are my resonant vectors. I have a conservation of momentum condition here that was from the beginning, and then I have a conservation of energy condition here, and of course, I'm summing over all Rn, and I'm assuming that I'm doing a cutoff. So my resonant system, or my resonant part, or my resonant vectors, or what I'm summing over here, also have the condition that all of my indices, or all of my wave numbers are less than or equal to n. Again, because I essentially threw away the higher the tails of the sequence. Okay, so this R, or these resonant terms, this is what I essentially care about the most. Essentially, this should, in some sense, completely determine the dynamics of the system. And what we would like to do is say something about what this tells us about the flow. Okay, and so let's look at that really quickly. What do these K1, K2, K3, and K4 quadruples look like? They can take two forms. Okay, and these are two examples that satisfy these two conditions here. K1 plus K2 equals K3 plus K4. These are all, and this is my dimension is going to be 2 here, but these are all two-dimensional integer vectors, let's say. And my lambda K1 and my lambda K2 and my lambda K3, these are going to be, I think I defined, oops, I'm going forward, not backwards. I defined it here. Okay, so it's almost an L2 of my frequency vectors here. Okay, so what do these look like? They either a box, which is very nice. They either form in this nice kind of rectangle, or they can form this weird kind of diamond shape. Okay, and one can say, or one can show, that essentially the shapes here that you can get from these quartets determine whether or not you have a propagation of energy from small modes to high modes, or an increase in turbulence, let's say. Okay, and so essentially this tells us essentially that you can have a growth in your Sobolev norm with these shapes. And so how does it happen? Okay, so let's take an example. Let's say I have P1, P2, P3, and Q1. what I can do is I can form rectangles here. I have forming two rectangles, one on the right side and one on the left side. So if I start off with energy, let's say my initial condition, I have activated the modes at P2, P1, and Q1, then energy should pass to Q2. Okay, so because I have interactions between those modes, all right, given in my resonance system. And moreover, since I've activated P2, Q1, and P3 at time 1, I should have energy passing to Q3 as well. Okay. Okay, so far so good. All right. So I started off localized at P2, Q1, P3, P1. I've moved to Q2 and Q3 as well, but I haven't moved too far away. But I can take Q1, Q2, and Q3, and I can form this diamond shape here. And now my interactions are between Q1, Q2, and Q3, and Q4. So I have energy at time step 1, let's say. This is not exactly how it happens because you have infinite speed of propagation, but regardless, at time 1, let's say, or at the time step 1, you have activated Q2 and Q3. Now you can pass energy from Q1, Q2, Q3 to Q4 because they form this nice diamond shape, let's say. Okay, and the energy can pass along this way depending on what type of shapes your resonant system or your resonant quartets demonstrate. Okay, using this type of thinking, in 2010, Carl and Taurus essentially demonstrate that you can show individually or specifically that as time goes along, energy passes in this way. It's not a very easy thing to do. Again, as I said, immediately after time 0, you have your 0th mode interacting with your 1,000,001 node, essentially, right? So you actually have almost immediate kind of the ability to immediately transfer energy to higher modes, arbitrarily higher modes. But if you are very careful, you can show that it kind of grows in a very nice way, as they do in Carl and Taurus. And this is again for the square case. So this is like for the square case, you get both diamonds and rectangles. Okay. For the irrational torus, let's say. Okay. What happens for the irrational torus? And again, this is the truncated Hamiltonian system, the exact same thing we had before. What you can say for the irrational torus is that if you start off localized in a small enough box, and I'll describe what Q sub m is in the next slide. If you start off localized in a box, you can't have energy escape to higher modes. Okay. Right. And so you can't have this process. Oops, excuse me. Keep going backwards. You can't have this process where you start here in this box here. You move to Q2 and Q3, and then you move to Q4, essentially broadening the support, your Fourier support of your function or your sequence, essentially over time. And what we were able to show in 2019 is that you can't do this for the irrational torus. Okay. For the irrational torus, you start off localized in a box, and then you essentially stay in that box for all time. Okay, but not for all time. For solutions that are analytic in time with respect to this new truncated Hamiltonian, right? So this was kind of, I guess, surprising to us, but also a little bit annoying, because again, for well-posedness, your solutions do not need to be analytic in time. We would like to demonstrate that for kind of arbitrarily long times, you don't have this transference of energy from low modes to high modes. And so at this point, we were, a little, we were happy that one can show that for the irrational torus, you have this very different behavior than you did for the rational torus. But we still have this barrier that we need it to be analytic in time, which really limits your, for one, it limits your time scales, but it also limits you to considering only very small data. because only very small data will be analytic in time for a very long time. If you have big data, big initial conditions, and big in the HS norm sense, then there's nothing, or you essentially can say that it's all of this occurs in a very small time scale, which shouldn't really be the case, or at least that's what we thought. Okay, and here's a picture of what I'm drawing here. This is my QM, it's a nice cube. I have these modes activated at time 0, and then I have this weird picture that says that you cannot pass from you cannot pass energy from this initial box to outside of this bigger box here. I will also at this moment say that it was nice to start working with someone who cares about the visual representation of their work, because these are hard for me to do, these pictures. Anyway, so what can we say about the total system is that in a certain time scale, then you have essentially the opposite of what Carl and Faux says, what they say for their system. And I won't dwell on this. I'm running out of time as well, and I have some pictures that I need to show here. But essentially, this is the opposite of what Carl and Faux say, and it demonstrates that essentially you cannot at least easily show that you have a propagation of energy from low modes to high modes. Okay. Now, again, as I said before, we needed analyticity in time, and this was annoying because, well, because that means time can be necessarily short for very large data, and so as a kind of a continuation of what the 2006 result or 2010 result, excuse me, on the growth of Sobolev norms, Guardia and Koloshin proved in 2015 that you have a kind of quantitative growth in Sobolev norms. And I think I'll be really quick here. And this is this is a little bit more quantitative and demonstrates exactly how you can grow. What Gigliola and I also prove is that you can't actually do this same type of construction of solutions that grow in time. And so again, and this is a lot here, but let me go back to this picture here. This is a very simplified, diagram of what's happening and how you pass from low modes to high modes, okay, in the rational case. In the paper of Gigliola et al., they construct these very, very confusing families and generations, and they show that if you're localized in one generation, let's say lambda 1 of indices, then you eventually pass to a larger or further generation of indices. And these indices actually are further along, or sorry, they have higher, these indices are higher, sorry. And so you have to construct these very, very confusing conditions to ensure that you spread from low modes to high modes. Again, I said I would be quick on this. Essentially, as part of this, Guardia and Koloshin show that essentially the nth generation, the energy of the nth generation is much bigger than the energy of the initial generation, really. And then we show that in the irrational cases, it's impossible to construct these families. Okay, so I said that I would be quick with that, and I'll leave it there. But the question, of course, now, does propagation of energy occur eventually, in particular after time, after analytic time of existence? Do you then begin to actually pass from low modes to high modes? And what happens when the initial data is not small, which is something, again, that was hard for us. Okay, and so now when we started collaborating with Yulin in the summer, he showed us these numerical simulations. All right, so you're starting off with a initial condition that is very, very highly localized, really near the 0 4/8 mode, but 1, 2, or the ones that are just 2 distance away from the origin here. And over time, your distribution of your Fourier energy, essentially, or your energy essentially goes to higher modes, but it kind of has a barrier. They don't transition from low modes to high modes after a certain amount of time. And if you have a smaller size initial condition, and the size is in HS, then essentially, again, you're localized. You stay localized forever. And the localization is even stronger when you have a smaller HS norm. Okay, and he did a simulation for the irrational torus as well. And this does exactly what we expect. You start off with a localized solution, and this is what Carl and Falou show, this is what Guardi and Koloshin show, this is what Staffilani had also, that you start off with localized in Fourier space. You can transition to higher modes, and the distribution gets even more and more wide and wider and wider. And again, it kind of tracks with how large your HS norm is. And for Gigliola and I to see things like this, it blows our mind because no one ever visualizes what's going on when we do pure math. And so we were just like super excited, and also to have something to actually demonstrate, having an opportunity to actually show, or let's see how do I describe this, having an opportunity to be informed about our decision making when it comes to what we want to actually prove. A lot of times you're basically just grasping at straws, or just like searching around in the dark for something to show itself. But when you have the opportunity to see some simulations, it kind of clears your mind. And so what we did, once we saw this, we figured that what we wanted to show is very different than what we were shown before. What we wanted to show is not that we have this type of almost periodic, what we can show, or at least not. And I should also mention that this is for a two-dimensional Schrodinger equation. The aspect ratio here is like 1 and the fourth root of 2 or something like this. Regardless, okay, and that's not good for these two. That's what the aspect ratio is. All right. What was I saying? So we wanted to show that essentially, for at least high regularities initial conditions, you don't pass. You don't have a situation where you can't pass the higher modes at all. What you should be able to show is that there is a barrier at something at which you cannot pass at all. So not that that if you start in a box and you stay in the box, but you maybe can grow your box a little bit. You can grow your support a little bit, but then it actually stops. And so what we did was we said, well, what we want to do is kind of demonstrate that this happens in a logical way, or actually that has some mathematical foundation. And so we said, well, okay, but what type of data are we looking at? We're looking at very high regularity data. We're not looking at data that's generally speaking in a finite space. We're looking at very, very specific, very, very regular data, essentially initial data where your Fourier modes are concentrated or a bounded set. Your Fourier support, excuse me, is in a bounded set. And so these are classes of functions that are not just in HS, that are not just have 10 derivatives. They're analytic, but even if you look at the analytic Banach spaces, the Gevrey spaces, they're in all of those as well. So we were looking for something that is not really what typically you would look at for for a result like this, in the sense that instead of looking at saying all HS data with a small enough HS norm satisfy this condition, we're saying that a very dense subset of HS data with the arbitrarily high initial condition in the HS norm satisfy exactly what we want to, or you can show that it doesn't have a propagation of energy from low modes to high modes. Okay, so yeah, okay, so and we also, okay, so, and this is a part of it as well, that we know that our initial conditions are analytic. We know that the solutions essentially should be continuously analytic, but we want to show essentially that not an analytic lack of energy propagation, but just the HS lack of energy propagation. And so again, I'll be able to quick here. We do a different change of variables, one that loses some derivatives, which is a whole story that I could talk to you about for a long time, but I don't have much time. But we do a more fragile change of variables, but for a smaller subset of phase space. Essentially, this is the best way to describe it. It breaks if you consider every element in space, but if you consider a very specific element in specific elements in space, including those which are demonstrated in the, or used in the simulations, then you can demonstrate that you actually do not pass. You don't have transfer from small frequencies to high frequencies, or you don't have turbulence really. Yes, so yeah, that's generally speaking what's going on. And this is more or less a summary. There are a couple of things that I didn't discuss very much, small divisors in general, but this is a very technical piece of what we do. But again, as I said, we're defined only on a dense subset of HS. We have energy that may transfer from small frequencies to other small frequencies, but that's what was demonstrated in the simulations. Because we're doing a kind of we're assuming that we are on a smaller regularity subset or a dense subset of HS, we can take arbitrarily high HS norm data. And then we do have to do one also technical thing, and that is we must assume our rational vector is actually algebraic. But we use our Ross theorem. And then what we can show is this, that for the new truncated equation with the new normalization, that your high modes stay very small, okay? That you don't have, and in particular, if you start off with 0, then you'll stay 0 forever. Your HS norm of the higher, or the higher cutoff, or the tails, let's say, okay? Okay, yeah, I'm running out of time, so I don't want to take up too much of your time, but some other questions, whether we have integrability or not, this is a very hard question. Is it truly an integrable system when you're talking about HS, or we're talking about the irrational vector or irrational torus? Integrability is a very hard thing to show, and generally speaking, for example, if you want to show the KBB is integrable, you can write a book on just that whole proof. If you want to show that cubic NLS is integrable in the dimension 1 case, again, you're going to have to write another book and still leave out a lot of the information. And so it's a really long-term solution or long-term goal. Again, we still need to know whether or not energy propagation occurs ever for the complete system. For the normalized system, it doesn't, but for the complete system, it's not clear. And again, best way to articulate for the implication for the unnormalized system and the untruncated system. And of course, and I should note this is the last thing that, and it's the last interesting thing, I suppose, is that we want it to have a very clear understanding of how the size of the initial data, the HS norm of the initial data, affects essentially the radius of the Fourier support after a long time. And we think it has something to do with somehow like log of the HS norm somehow is related to that, but we don't know exactly that yet. And last thing, and the thing that we're always considering is what about quantic NLS? What about higher order nonlinearities? All right, thank you for listening. Sorry, okay, I took too much time probably, but thank you very much for listening.